Hello, y'all. Welcome to Lesson 17, Structure 1.4.5. Today, we're going to be talking about molar concentration, specifically how it's determined by the amount of solute per the volume of solution. We should, by the end of today, be able to solve problems, including involving molar concentration, amount of solute, and volume of solution. We will be using square brackets to represent molar concentration. You should be able to include units of grams, decimeters to the negative third, and moles, decimeters to the negative third, and convert between the two. It's a lot easier than it looks. The relationship N equals C times V. That will be in your data booklet, so you don't have to memorize it. However, it's kind of self-explanatory given the units, and we'll talk about that as well. So with that said, let's go straight into molar concentration. And as a little extra, we're going to talk about standard solutions at the end of this as well. So, why are we talking about concentration? Well, when you think of concentration, you usually think of concentration of a liquid, like you might be making some orange juice, which is just orange juice particles in water. If you're making it from concentrate, you might have some orange juice particles, and you mix that with water. In this case, your orange juice particles, which let's just so helpfully color this orange, is your solute. Solutes are things dissolved in a solution. And I abbreviate solution SOLN. Water is your solvent. It's usually the thing doing the dissolving. Water is a great solvent. It's also referred to usually as the universal solvent, because it's so good. And we'll discuss later why it's so good when we talk about intermolecular forces, but it's really good. Now, when we have a solution, we generally also refer to that as an aqueous solution. You may remember when we're talking about states of matter, we had AQ, which just means that the thing that is AQ is dissolved in a solvent. Anyways, so we're coming back to particles and we're talking about concentration. Usually something that's more concentrated will have more particles versus less concentrated. Another word we use for less concentrated is dilute, has less particles. So if we have the same liquid in either case, so let's just say we got some liquid, the more dilute one will have less particles. The more concentrated one will have more particles. And you might be like, well, this is kind of obvious, but it's something we need to be able to use in terms that we should be able to use with confidence. So we're just going to go over that a little bit more. And what is concentrated exactly? Well, what is concentration? Concentration is actually a very scientific term, concentration, and concentration is specifically the amount of particles of solute per volume of solvent. Now, there's some keywords here that you might have noticed: amount and per volume. Now, in chemistry, we generally use something for amount. So the concentration of a substance, which once again we use concentration of square brackets. So maybe concentration of X is equal to mole of X per volume of solution. So not the solvent, but the entire solution together. That is concentration. Another way of expressing it, as per your data booklet, is C for concentration is equal to N uh, divided by V, where C is once again concentration, N is mole solute, and V is volume solution. We use very specific units for this. Concentration is measured in the units of mole, decimeter, -3. In other words, mole per decimeter cubed. So we use decimeter cubed for volume. A helpful hint about decimeter cubed is, and this is something that you should be really good at remembering, decimeter cubed is equal to liters. So 1 decimeter cubed is equal to 1 liter. Same thing with 1 centimeter cubed is equal to 1 milliliter. These are just some helpful hints that you should keep in mind. So this is measured in the units of mole decimeter cubed or mole per decimeter cubed. But we're going to get used to the one on the top because IB does not like to put things on two lines. Furthermore, moles are clearly in mole and volume is clearly in decimeters cubed. This makes sense that when you take mole and divide it by decimeter cubed, you get the units mole per decimeter cubed. Turns out dimensional analysis is the best way to kind of handle any molar concentration problem. There is one more way concentration is expressed by the IB. However, this is far less common, so we're going to do a little aside, especially because this is not done in labs, not in chem labs. Chemists hate this, and I do not understand why it's in the DP curriculum, but it is, so we're going to go over it. It is another type of concentration where its concentration is equal to mass over volume, which provides you with the units of, and I'll use purple for units once more, grams decimeter -3, where this is grams of solute, ridiculously enough, and this is decimeters cubed solution. And you might be like, well, why do you hate grams so much? And it's because you can't compare grams. If I have, like, this is the absolute most ridiculous thing, but I'm going to go on this aside just because the DP finds it important. If I have 10 grams of sodium chloride and 10 grams of magnesium chloride, and I put them both in 1 liter, or sorry, let's use DP terms, 1 decimeter cubed and 1 decimeter cubed of water, and we make, let's say, approximately 1 decimeter cubed of solution, this would have a mass concentration of 10 grams per 1 decimeter cubed, which is 10 grams per decimeter cubed. And that would be the same for both. You would say these are equally concentrated. But here's the kicker. Sodium chloride has a much lower weight. This is about 58.44, while this one is about 100 and I think it's about 100 grams per mole. I don't have that exactly, grams per mole. This one I just have memorized because I use it so much. But because of that, we actually have more salt in here. There are more salt particles, while there are less here by about 2 times. This has about 2 times the salt. So using mass doesn't give you an accurate perception. Mass concentration does not give you an accurate perception of the liquid, and not comparable anyways. But the DP wants you to know it, so it is covered in this section, and that is about the extent I'm going to cover it here. We're going to skip over to the far more often used concentration, which is technically called molar concentration. So, concentration. I will reiterate this one because it's far more important. Because when you go into a chem lab and you make some solution, so, oops, let's say we have a bottle, it's going to have some liquid in it, and it'll have a nice little label. And then it's going to have some numbers that are like 0.3 mole decimeter cubed. And that's what it's going to say in your chem lab. It will always give you a molar concentration. So that's what we're going to use. Once again, that equation is concentration is equal to moles over volume, or in other words, moles are equal to concentration times volume. So with that said, let's just go ahead and do some examples with it. The example we're going to start right off the gate is what amount, I'll mark this as an example, what amount of magnesium bromide is needed to create 200 centimeters cubed of 0.0500 mole decimeter cubed solution. It seems really complex, but we're going to break it down. So the question is asking for an amount. An amount automatically signals to me that we're looking for moles. Furthermore, we're given two values. We're given a centimeter cubed value and a mole per decimeter cubed value. And so when I look at these, I identify this as a volume and I identify this as a concentration. So knowing that I want moles and I have a volume and I have a concentration, I'm going to use this formula up here. Moles equals concentration times volume. So N equals CV. Now, you may notice that there's a little hitch here. My volume is in centimeters cubed, but my concentration is in decimeters cubed. This happens often because centimeters cubed, like I said before, this is equal to milliliters. And a lot of your glassware, a lot of the products you use in your lab measure in milliliters. However, the DP likes to measure in decimeters, so we have to convert between the two. That's all right. We have learned that 1 centimeter cubed is 1 milliliter, 1 decimeter cubed is 1 liter. And I know that to go from a milliliter to a liter, 1,000 bits. So 1,000 centimeters is therefore equal to 1 decimeter. So I'm going to keep that conversion in mind. 1,000 centimeter cubed is equal to 1 decimeter cubed because I know that 1,000 milliliters is equal to 1 liter. So what I'm doing is I'm converting from units that I'm used to, milliliters and liters, into units that the DP likes. Specifically, when I say units that I'm used to, I'm talking about these, which are also what all your glassware is going to say in your lab. Regardless of what lab you're at, your glassware will measure in milliliters and liters. So I'm going to keep this conversion in mind. Honestly, if there's anything to memorize and just have off the top of your head, it's this. Also, converting between them is quite easy. All I'm going to do is move my decimal over 1, 2, 3 spots. So now I know that N is equal to my concentration, which is 0.0500 mole decimeter inverse cubed, times my volume, which I also now know is 0.200 decimeters cubed, and I've done that conversion. I find that my decimeters cubed cancel with my decimeters inverse cubed, which will leave me with the unit of mole, exactly what I'm looking for. When I plug this into my calculator, or you may just automatically recognize, this is 0.0100 moles. Therefore, I can say I need 0.0100 moles of magnesium bromide. And there you go. You have solved a molarity problem or a concentration problem for your solution. The last part that the DP may ask you to do, not may, they will ask you, is they're going to say, well, we measure things in a lab by volume or mass. And unfortunately, as we learned from a previous unit, moles is not a volume or a mass, so we must interconnect and we must convert. So what we're going to do is we are going to find the mass of magnesium bromide needed. That's a lot easier than you might suspect. It's 0.0100 mole magnesium bromide, and we're going to use our molar mass. I know I want mass, which is grams, and I need to get rid of my moles, which will be on the bottom. Using my periodic table, I can find that the molar mass is 184.11 grams mole inverse. That's two bromines and one magnesium added together. So I'm going to multiply by 184.11 grams per 1 mole. My moles will cancel, and I will get an answer of, once again, I notice that this is 0.01, so I'm just going to shift my decimal, 1.84, and I'll drop the 1 grams of magnesium bromide needed. So when you go into your lab to make this solution, specifically 200 milliliters of the solution, all you need to do is add 1.84 grams of magnesium bromide and then fill your beaker or whatever to 200 milliliters. And there you go. That is our answer. This is definitely something you should practice. We'll do a lot more of it in your classes as well as over the course of other examples in this text. But that is molar concentration done. We're going to go over to our added bonus of standard solutions. Standard solutions are just very much precisely measured solutions to contain an exact concentration of solvent, or sorry, not solvent, solute. Now, that's very important in our lab. Within your lab, much like I mentioned before, you're going to find a lot of reagents, usually in an aqueous form already. So you need to be able to make these reagents to have a very precise amount of solute. Otherwise, all your reactions will be off. So how do we make a precise standard solution? Well, I'm going to use an image, whoops, that I pulled straight from Cognity. Thank you, Cognity. And we're going to go over each step and annotate it because there's a couple things to clarify. So first off, before we do any of it, we need to find our desired concentration and volume. So like, for example, you might want to make 1.00 liters of a 0.500 mole decimeter cubed solution of salt water, NaCl. You'll notice that we have a precision of 3 significant figures on each of these values, which means that our instruments must be that precise as well. If you don't have a good grasp on significant figures, just note that these are very precise numbers having multiple spaces after the decimal. So the first thing we need to do is calculate the mass we need. And when we do that, we need to use a very specific sort of mass balance. Generally, you want something that goes to the 0.01 gram, or if even better, 0.001 gram. And you weigh out your solvent or solute in a beaker. What you'll notice is then you dissolve some of that solute or dissolve all that solute in water. You can use a stirring rod or you can just swirl it if you're using an Erlenmeyer flask, but you're going to dissolve it. But the very specific thing here is you will not add all your distilled water. It's very, very important that you don't just put in a liter because you need to then use a volumetric flask. Volumetric flasks are incredibly precise, incredibly precise, but they only give one volume, give one volume. So must use a volumetric flask equivalent to the volume you're looking for. Something else that you have to do is once you've transferred that liquid, there's always a couple drops left over in the beaker. And those drops contain some solute that you did measure out. So you must use a spray bottle to get that out and pour it into your solution. Anything that ends up touching your liquid will need to be sprayed down, including the funnel. And this is why you don't want to fill all the way, because you're going to be adding water to constantly clean and rinse different aspects, and your volume of liquid will go up. Finally, when you finish cleaning everything, you're going to add liquid in up to the volumetrics line. Generally, you want to use a pipette, something precise, because with a volumetric flask, you cannot, cannot go over the mark. If you do, you've added too much liquid, and then your entire equation is wrong because now you have too much volume. And any amount of volume you try and remove will also contain your solute. Therefore, your entire solution will be off. So you must be precise as you fill up to your line. Lastly, you just stop it and you invert to mix. You generally just invert it a couple times. So this is how we make very precise standardized solutions. A good standardized solution usually has three sig figs, so 1.00 or even more mole per decimeter cubed, maybe even more to 1.000 mole per decimeter cubed. It's kind of hard to get that specific. You need to have specific tools for it. But otherwise, I hope this helps and have a great day.